Hello, welcome to the solar design course. I'll try to keep this within 10 minutes. Just going to give you a brief overview of the parameters to consider, factors to consider, a brief overview of how to choose components, and subsequent lectures. We'll look at a more in-depth design. We'll use Python. I don't really want to use Excel, so I'm just going to use Python. Probably going to use PVSys in another one, but mainly it will be Python because that's free and PVSys is a pay-for software. Anyway, without further ado, let's look at the important parameters and how you go about deciding on which panel to use and whatnot. So we look at important parameters before we actually go on the types of solar panels. Actually, let's start there. You get different types or different chemistries, so to speak, of solar panels. And these differ in efficiency, they differ in price per kilowatt, they differ in lifespan as well. The most efficient chemistry that we have commercially, I'm not talking about research or stuff that is used on the International Space Station. I'm talking about the stuff that you can go to a store and buy, will be your PERC panel. That stands for passivated emitter and rare cell. It's about 25% efficient. It has the highest commercial price per square meter. That doesn't look right. Yeah, actually it does. It has the highest commercial price per square meter, but the price per watt is similar to monocrystalline or even lower in some cases, depending on how good a deal you get. So typically, you'll use this type of cell or this type of panel in areas where you've got very little roof space or areas where you've got very little space because it's the most efficient and therefore you won't need that much space in order for you to generate a lot of electricity. Typical lifespan is 25 years. Second most efficient commercially available panel is a monocrystalline. This, by the way, is an improvement of the monocrystalline. A lot of what you find here physically exists here. It's just that this has some extra stuff to give you more bang for your buck. But more on that in other videos. I'm not going to be discussing the actual physics of how these things work. The monocrystalline is about 25%, sorry, 20% efficient. It has the second highest commercial price per square meter, but the price per watt is similar to this, or in some cases, it might even be higher, but it is definitely higher than your polycrystalline, which we'll discuss next. This is also used in areas where you've got very little space available. And like the PERC, it's also aesthetically appealing because it has that consistent black color, you know what I mean? Instead of that bluish color that you get on a poly. And lifespan is similar to the previous cell. The polycrystalline is about 15 to 70% efficient, but this will give you the best bang for your buck. What do I mean by that? It is the lowest watt dollar per watt price, so to speak. So you really do get the best bang for your buck. This is typically used in areas where space isn't much of an issue. So if you've got plenty of roof space and space isn't an issue for you, then this could be an ideal candidate. Similar lifespan as well. And then we look on to something a little more novel. Well, it's not necessarily novel, but it does have complications, and that's cadmium telluride. These will have an efficiency of about 9 to 11%. The price per watt is slightly lower than polycrystalline. So this is gonna give you actually better bang for your buck, right? Wrong. You'll see just now why this is actually more expensive in its lifespan than polycrystalline. It has the best energy payback period, lowest carbon footprint, but the toxicity of cadmium makes it very difficult and very expensive to recycle. And that's the number one reason why residential and probably industrial users will not even consider this because A, efficiency figures are low, and the toxicity of cadmium and the costs associated with that just don't make it worth it. So you'll find it in old-fashioned power stations. Um, these were used in old-fashioned power stations where the cost of disposing cadmium is a bit less than the benefits obtained from using the technology. The lifespan is about 25 to 30 years, so you do get it. It is a little bit better than the other chemistries, but only slightly. And then if we delve over to the thin film range, we've got amorphous silicon. This is the sort of stuff that you see in calculators. If you've got a calculator like this one on your bottom screen over there you'll see the sort of chemistry that I'm talking about, and that's your amorphous silicon. They have one of the lowest efficiencies. I mean, we're looking at about 6 to 8%. As for the price per watt, who cares? Because you're only going to use it for small applications anyway. But just kidding. You do get better prices, but it's sacrificed. It's at the cost of efficiency. So you can't really use this on a large scale, not efficiently, not optimally anyway. And like I said, it's used for pocket calculators and other small devices. And the lifespan is only about 10 years because who's going to keep this stupid calculator, this intelligent calculator for 10 years anyway? So who cares? And then the best efficient thin film available commercially, I'm not talking about research, would be your SIGs, or some people will call it KIGs. And that's copper, indium, gallium, selenide. Goodness, I'm not a chemist, I'm an electrical engineer. That's about 13 to 50%, 15% efficient. Like I said, it's your best film bang for your buck, but its price per watt is still higher than poly and monocrystalline. It's usually used for solar shingle tiles. So those little roof tiles that you get on top of your houses, which have solar panels on them, that's usually the SIGS technology. And the lifespan is similar to the others as well, and that's about 25 to 20 to 25%. Right. So let's actually look at the parameters that we consider when we choose these cells, or rather when we've chosen these cells, we look at the design parameters that we have to consider. One of those design parameters is your open circuit voltage. So your open circuit voltage is typically the maximum voltage that you can obtain from that panel, and that's usually obtained when you've got no load connected across it at standard test conditions. More on that later. Your short circuit current is usually written as ISC. That, by the way, is written as VOC. This is your maximum current that you would obtain if your terminals were short circuited together. So if you were to just slap an ammeter there under normal test conditions and short circuit those terminals, that's the current that you would get. Sorry, that's standard test conditions. There's a very big difference between NOCT and STC. Then your power rating, this is the maximum power that can be obtained out of that solar panels at standard test conditions. I think that's about 25 degrees Celsius or 20 and 1,000 watts per square meter or something like that. It's usually written on data sheets. There's a difference between STC and NOTC, but more on that on the actual design course. And this value is affected by multiple factors. Factors such as temperature will affect it, irradiance will affect it, and that is a subject on its own. When we talk about irradiance, there are a lot of factors to consider, but I'll take you through the important factors in the design course, subsequent lecture. Albedo and many others. When we talk about albedo, we're actually talking about the reflective index of the surface. So a red surface won't reflect as much light as a white surface. Snow, for instance, will have a higher albedo and so on and so forth, but more on that later, like I said. Then the important bit is the maximum power point. This is the maximum power that can be obtained for that load level. So if you've got a 5 ohm load connected across that panel, this is a figure where you would obtain the maximum power across that 5 ohm load. And I'm actually going to illustrate this with a diagram. And by the way, I actually do have a YouTube video that discusses this in much greater detail, where I actually even use Python to sort of simulate it. I've got flow charts, I've got all of that. I'm going to link it somewhere here or there or here. but the link will be in the description as well. It'll appear somewhere on the screen too. Nonetheless, if we look at this over here, and let's assume that we're pulling current at this dotted line, right? But our voltage, the voltage at which we deliver this current is only somewhere here. So effectively, we'd only be getting this much power out of our panel. Even though this panel has the potential to deliver this much power, but we're only getting this much power. And that's where MPPT comes from, because it'll adjust the voltage by changing the duty cycle in the buck converter. Or boost converter, doesn't matter. It'll adjust the voltage such that you're always at this optimum power point or very close to it. As you'll see in that video that I linked you to, you have to click on that video. No, really, do click on that video. So yeah, that's what it does. It does adjust the voltage such that you get your maximum power point at any load. So if you're pulling this much current, it'll adjust the voltage such that you are at this optimal power point. Hope that makes sense. Right. Now let's get to the bricks and mortar of things, because that was just setting the groundwork. Let's look at the types of installations. You have grid-tied installations, you have hybrid installations, and you've got off-grid installations. Let's start with grid-tied. What do we mean by grid-tied? A grid-tied installation is something like this, where you're generating power, you're generating power, energy, whatever, from your solar panels. Actually, you can't generate energy. It violates the first law of thermodynamics. Doesn't matter. So you're generating whatever you're generating with the solar panels, goes through an inverter, and that inverter just converts that DC to AC. And you use some of it in real time in your home. So you'll use some of it for your TV, for your lights, for whatever you need power for. But some of it, the excess, what you're not using, will be sold back to the utility. So you're actually selling power to the government. And this is subject to local regulations. In South Africa, it's still a huge area of debate, and I don't understand why. But essentially, this is a DC, a grid-tied system. So you're using power in real time, and what you don't use, you're selling back to the grid for somebody else to use. But it's not always the most optimal. It's not the best way of going about this whole green energy thing, but that's a topic on its own. There's a lot of debate on this system, and you'll find that the feed-in tariff, the rate at which you're selling, is far less than the rate at which you're buying. And that influences your decision as well, your ROI, if you're going to look at financial feasibility. Second chemistry, or the second topology, is the most expensive topology because you need storage. So basically here you've gone off grid. You're not using utility power anymore. How you go about doing is you're generating electricity from your solar panels and you're using it in real time. But what you don't use, you store in batteries so that you can use it when solar energy is not available. And you need to size your batteries such that they have enough autonomy to last you beyond the point where solar energy is not available. Also should be able to last you during cloudy days. And that's why this system is very expensive, because lithium ion batteries or AGM batteries, deep cycle batteries, those don't come cheap. Their lifespan is also not as good. So this kind of system is very expensive, and I wouldn't really recommend it except for exceptional cases. Then a third system, which is a compromise between the two, so it sort of gives you the best of both worlds, at least some would think. This has your storage, your battery storage, like the off-grid system, but you're also feeding to the grid. So what actually happens here is you're generating electricity, you're using it in real time in your house. What you're not using, you're storing in your batteries, and your batteries are full, or the excess still goes back to the grid. So some of it goes to you. The number one priority will be your house, second priority, charging batteries, and third priority, the grid. Or you can play around the settings. Most inverters will let you play around with the settings as you wish, because you can actually still draw power from the grid here as well. which is something that an off-grid inverter or an off-grid system will not allow you to do. So this sort of gives you the best of both worlds. And in terms of cost, this is the second most expensive. This is the most expensive. And right now, or at least in some countries, this is the cheapest system because it doesn't include batteries. But that's a subject to debate, particularly in the Banana Republic, which is where I happen to be from, aka South Africa. This would be probably your best residential application or residential system, because we've got load shedding, and that is a political problem, not an engineering problem. This is what happens, by the way, when you get a bunch of politicians to run an engineering facility like Eskom. More on that another time. Right. So other important concepts that we need to look at include the way in which we structure these panels. We'll talk about a string. A string simply relates to or refers to the number of panels that you have connected in series. If you remember those batteries that you used to connect in series in primary school? Yeah, similar concept here. So if you collect a bunch of solar panels in series, then the maximum voltage rating of that panel, of those panels, is the sum of the individual voltage ratings of each panel, right? So if your VOC here is 20 and there it's 20 and there it's 20, meaning your total VOC over there is going to be 60 because you've essentially connected these in series, right? And if you were to connect these panels in parallel, then the voltage remains the same, but the current rating will increase. What this essentially means is in a string, if you've got a string of of 3 like this one, and the VOC of each panel is 20 volts, that effectively means that your total VOC is going to be 60 volts. However, your ISC, that being your short circuit current, is still going to be the ISC of the individual panel. So if your ISC for one panel is 10 amps, then guess what? The ISC of this entire string is going to be 10 amps, because the current that flows through this panel is the same as the current that flows through here. It's the same as the current that flows through there, right? So if you get a fuse in here, that fuse has to be rated at 10 amp plus 10% or whatever your local regulations will stipulate. But you'll get a feel for these things when you actually do the design work. It's not as hard as it looks. And the limiting factors of how many panels can you have in series? Because let's look at it this way. The more panels you have in series, the higher the potential difference, right? Or the voltage. And that means you won't need as many units in parallel to get to that higher current. And that means your cable size as well will be lower, because if you're transmitting higher currents, then you need a larger cross-sectional area to be able to handle that current. And so we want to go as high as possible with the voltage so that we can save on that little copper space or the current requirement. Right, but can we generate 1 or 10 kilovolts or 100 kilovolts? Can we do that? Is it practical? Well, it's limited by voltage regulations in your country. In South Africa, that's going to be something like SANS 10142. There's an NRS regulation as well that is meant specifically for SSEG, that's being small scale embedded generators. I'm not going to be discussing that. Also, your insulation requirements. The higher the voltage is, the thicker the insulation has to be, right? And that's going to be more expensive. So there is a trade-off that you have to consider here as well. And most importantly, your maximum inverter DC voltage. You don't want to be generating 100 kilovolts here when your inverter can only tolerate 1 kilovolt maximum, because you're going to burn that inverter, right? So your maximum DC input voltage also dictates how many panels you can have in series. And lastly, your inverter maximum power range. Many inverters will have a typical power range where a typical voltage range where they operate optimally. And that's usually for your high voltage inverters, rather not high voltage, your low voltage inverters, that's usually going to be about 500 to 800 volts. but feel free to consult your data sheets on that and consider those as well. So all these limiting factors have to be taken into account when you design an actual system, but you'll see that when you design an actual system in the next video. Right. What else do we have to look at? We also have to look at combiner boxes. What do these combiner boxes do? When you have multiple strings like this, instead of using an inverter for every string, if you want to connect a bunch of these in parallel to a common bus, that being a bus bar for your electricians, if you want to connect all of these in parallel to a common bus, so sort of add them, then you can use combiner boxes. Typically going to use to connect multiple strings. If you've got just one or two strings, you can just slap those in parallel and connect them to the inverter. That's not the most optimal way of doing it, because if one panel is shaded, then you're suffering severely. More on that later. So combiner box will be used in a typical arrangement like this, where you take all of this to a combiner box, which will have which will have the diodes, and those diodes will typically prevent current from flowing back into the strings and causing hotspots. So that's sort of an advantage. You're also going to have circuit breakers and or fuses, and that will basically isolate these panels if there's a short circuit or a fault that may occur that will result in high current being pulled or whatever the case may be. You'll also have over voltage protection or surge protection in combiner box. Not all of them come with surge protection. It's not a legal requirement in some places. I don't think it's a legal requirement over here, but I have to revisit my SANS 10142 and my NRS regulations as well. Right. The next thing that we're going to look at are MPPTs. Actually, I've already discussed this, and I'm going to link that in the description, the video that I spoke about in the description and in your card over there, or there, or there. Somewhere. All that matters is there's going to be a link to a video that speaks about MPPTs in a lot of detail, where I discuss the algorithms that I use to implement these MPPTs. Right. Now let's look at inverters. What do these inverters do? So this inverter will typically convert the DC output from your solar panel to an AC output that you use. That little laptop that you're using right now, that charger actually takes AC voltage. And then a lot of rectification nonsense will happen, but who cares? That kettle that you use to make hot water for your coffee, that uses AC. And the electricity that we use to light up our houses, that's AC. So AC is what we use, and DC is what is generated, and that inverter just converts that DC to AC. So when you size this inverter, it's largely dependent on the load that you're going to use, the amount of money that you're willing to part ways with, and the amount of risk that you're willing to associate with it as well. But typically, it's sized at 115% of the maximum power rating. So if you know that your panels will give you a maximum output of 5 megawatts, that's a lot, 5 kilowatts, then you're going to use typically 115 times that, 1.15 times that. Let's use our calculator quickly. And that's about a 5.75 kilowatt system. So maybe 6 kilowatt system for something like that. But like I said, the 5.5 would do okay as well. It's largely dependent on the load that you're going to be using, the amount of inrush current that you're expecting on your AC side, and the amount of overload that you're willing to tolerate as well. All right. So let's look at the impact of irradiance and why the solar panels only produce power during the day, not in the night. Right, so over here, we've got irradiance level. On the y-axis, we'll have your power, and on your x-axis, we'll have voltage. Right, so when your irradiance level's at about 300 watts per square meters, you're only producing for this specific panel about 50 watts. As the more your irradiance levels increase, the higher the power you produce. So your maximum power point over here at 1,000 watts per square meter, which is your standard test condition, you'll get your maximum power or your rated power, provided that the temperature is not high, it's still at STC as well. And if you keep decreasing, then your irradiance, so this will be typically around noon. It depends on when you get your maximum irradiance on the typical day when it's not clouded, because clouding does cause nightmares as well. But yeah, this is where you want to be. This is the best value during the day when you've got clear skies, bright summer day, summer solstice kind of thing. So yeah, that's what you get. Right. What if you've got shading? And shading can be caused by trees, it can be caused by by clouds and all of that. As long as you've got shadows that appear on your panels, and that will sort of decrease the irradiance, the incident irradiance on that specific part of your panel or that entire panel. And because those panels are connected in series in a string, that impacts the total output of the entire system. So that's bad. And I discussed this in more detail in the video that I linked you to. Again, it appears here or there or there or there or there or somewhere here. You're going to get a link also in the description below. Description is over there. No, it's here. Doesn't matter. So when you have partial shading, instead of getting this red curve over here, you're going to get something like this purple curve or even this blue curve, depending on the degree of shading that you have. And as you can see here, the maximum power that you can get is far less than the maximum power that you get on unshaded conditions. And it's also the MPP, or the global maximum power point, is much harder to track using conventional MPPT methods. But if you're going to use something that uses meta-heuristic algorithms, then obviously this is something that you can track. And again, I do discuss that in that video, so I'm not going to go into much detail with that. But yeah, these are things that you need to consider. You want to avoid shading at all costs, because you will not be getting as much money. You won't be getting bang for your buck if your panels are shaded. This is more than a 50% decrease in your power output. And over here, it's almost less than a 75%, almost more than a 75% decrease in your expected power output, all because of shading. And that obviously is affected by degree of shading and all of that, and how you've done your system. You're going to use microinverters and whatnot. But typically you want to avoid shading as much as possible. Right. Then we're going to look at the impact of temperature and why we want to keep these solar panels operating as cold as possible, within limits, obviously. Sometimes common sense is not common. People will go and freeze those things and then come back to my channel and say, but we're not getting power because they're frozen. Use common sense, good people, please. Right, so typically these tests are conducted at 25 degrees Celsius. And that's where you typically get your power ratings. And you will see as your temperature increases, the blue curve is your lowest temperature here. And the black curve, the temperature is a little slightly higher, and so on and so forth. So your power rating or your power output will decrease as you increase your temperature. So you want to keep these things as close to 25 degrees Celsius as possible. Even lower than that is fine. Just don't freeze them, good people. Don't freeze them. Even lower than that is fine. Actually, the lower it is, the better. So that's all there is to it. And obviously your VOC, your open circuit voltage, will decrease, and which is why the power output decreases. It decreases with an increase in temperature as well. So there's an inverse proportionality relationship in that. So in the next lecture, we're going to actually look at an actual design. And I'm going to go straight in with an industrial grid tie design, and we'll actually size these components. It's not going to be like the stuff that you usually see on YouTube that isn't very practical. We'll do an actual practical design for a real client. And if you'd like to get hold of me, I'm going to drop my Telegram handle below, and you can say hi. If you want to get a design done for your home or for your workplace or whatever, do say hi, and we'll send you a proposal. We'll look at pricing and whatnot. If you would like to sponsor this video, hi at me. Goodbye.